Hey everybody, I've been here again, and we're doing the second part, part B for our homework for, um, which the first part, if you remember, I used the iPad, so something new. Instead of the whiteboard, we wrote our derivation for our tank, 3 series tank on the iPad. So we derived the equation, basically utilizing Laplace transform. So we Laplace transform our drainage tank equation, and then we figured out how we could also utilize that to find the utilize that in the series of tanks, drainage tanks, and then find the change in height for our last tank in the series. So today, for part B, we are asked to for 3 tanks in the series with the inlet flow of the first and second tank. Use Jacobian to linearize the differential equation obtained in the state space A and B matrices. Then use SumPy to determine the transfer function relating to the height of the 3 tanks and inlet flow to the first and second tank. And then from this, we will we'll make a subplot, we'll make plots to then we can compare the response of a linear and a nonlinear model to the step change in a flow in the first tank. Okay. So basically we can kind of pick this off. So first, oh no, misclick. All right, first we can start talking about what a matrix C is. So a state space matrix C that we're using in this case is a component in a component in a solution to help try to solve for a what is it called? A linear invariant system. So invariant just means continuous. So for a linear continuous system, these are components that help solve for a system like the one we're doing right now. And as you see here, I pulled this from Wikipedia, but this is just general stuff. But the components and equations that we'll be using for our matrices are the ones right here. So our x, we're not using y today. I'll explain a little bit later, but these 2 equations are for our matrices for state space equations. These are the 2 key equations for this. So for this, we have our x, which is our x-axis for our state matrix, which is x dot because as you see here, we use x. We also utilize x as well. Represent something else, but we would need to just differential our x-axis for our matrix C out. So we have our x-axis matrix x matrix C depending on time, which is equal to A, which is our state matrix C, and then times our x, which is our state vector, and then plus B, which is our input matrix C, and then U, which is our input vector. As you see, everything is relative to time. Because remember, this is used for a continuous system, so time is definitely important to solving these type of situations. And then also we have second equation for our y-axis, for the y matrix axis. We have C times X plus D. To U, C represents our output matrices, and then D represents our feed through matrix. Um, but today we're just focusing on our top equation, the X. So we'll be only focusing on A and B, like it says here. Okay. And then we'll get to the transfer function later in our equation. But excuse me. But I already kind of wrote out our general initial code that we need. Um, of course, first we used our GitHub website to pull some of our data. So we imported our GitHub website, and then from GitHub we use our notebook. And then from a notebook we use CHE5 to import sim PID, then our transfer functions for 1 and 2, and then our shift. Okay. Some things we ought to also utilize was numpy as MP, our jacks. Like I said, we're using jacks Jacobian, but we also need to use jacks just in general. So we'll use jacks as JMP, and then subplots, of course, to plot our linear and nonlinear models. And then we're also utilizing SumPy. Um, and this will be utilized for uh, creating our transfer function equations later on in our Python. So we have some pi for our S, which I'll explain later. Um, and then the other one is kind of important. We have our solve VP because we have to put our uh transfer function into a solver before we put into our model before we represent our model, and then we have SciPy optimize for our root and minimize, mostly our minimize. Okay. All right, so now let's start our code. So for our conditions, we weren't really given any conditions, but we can just make up conditions. This is using the conditions we had in class. So our cross-sectional area is one. Our height of the hole, the cross-sectional area of the tank is one. The height, the area of the hole on the bottom of the drainage tank is zero point 0.2. Our gravity is 9.8, and then the flow coming in the top of the tank is 1. Okay. So first to start off, we just have to first explain our right-hand side equation. So we have to first this represent our equation for our drainage tank, which would be this bad boy right here. So right hand side, we do definition of right hand side. This should be our dependent variables with respect to time, height, but in this case, we represent this as V, which I'll explain later on as well. And then our flow in. So Qn initial. Okay. Next we will then utilize, next we have to, since we have multiple flows in, so because in our equation, in our statement, we have two flows in for the first and second flow of the tank. So we need for our Qn of 1 for tank 1. So a flow in for tank 1 and a flow in for tank 2. This would just be equal to Qn for our function. And then for our heights, since we have changing of heights, because our flows could be changing, we can change our height, our flows. We can also have set heights that we change as well. So we had to represent change the heights in our tank. So H1, H2, H3, and that will be equal to just V. And the reason why I'd use V because basically oh yeah, sorry. I was thinking something else. Basically our V we're gonna use H a lot in our equations, and I didn't want to get that mixed up just by using H. So we just use V instead of just saying OH. So all right. So now let's start. So first we want to run equations for our Q out. So we use our basically this AH square root of 2 times G times H first. So we will first record our flow out of our tank. So the flow out from tank 1 going to tank 2 is equal to the area of the hole um times and then we're using Jacobian, so it is JMP times square root uh 2 times gravity times height 1 for the height of tank 1. Yeah, that should be it. No, why is it giving me a squiggly line? Oh, it's supposed to be dot. Yeah, that makes more sense. Then we do it for all three things. So the flow coming out of tank 2 to tank 3 is equal to, it's actually the exact same equation as this, but all we're doing now is just changing the height. So H2. And then since we don't have no flow leading tank 3, we just say flow of 3, and then we'll just use this and change our heights. All right, and then next we want to then record our change of volumes for the three tanks as well. So we will be using this equation here for our change of volume, and then moving our cross-sectional area of the tanks to the other side just to have our change in height respect the time by itself. So that will look like, so we will do dH of 1. Oh, dH of one is equal to so we have N, so Qn of one minus Q out. So that'd be Q12 uh divided by our cross-sectional area of tank one. So again, they're all the same. So then we have change height two. We should do Qn one plus. Now we say plus here because we also have another flow, which remember in our equation, we in our problem statement you said there's another flow. There's an initial flow coming in into tank two, not including the flow draining from the tank above. So we have Qn of two, and then we'll subtract that by our flow coming out of tank two. And then this is divided by our cross-sectional area. And then, hold on. I think sorry, my recording messed up. Okay, we're good. Sorry about that. My back recordings was glitching or something. Okay, and then DH3 is equal to QN. There's actually this QN. No, it's Q of two and three. So the flow coming in from two and three, minus the flow three and divided by that's right. And then we're gonna turn all this for our function, and we'll put this as an array. So NP dot array. I do JMP since we're already doing Dracolian. Might as well just finish the JMP array of DH1, DH2, and DH3. Okay, should enter. Oh, why do I keep adding? My bad. Misclicks. Okay, that's gonna bother me. All right. So now we have that. We have our initial function. We have our function for our drainage tanks for all three tanks. Now we can start working out our matrices. Okay. So first we need to start with our steady state. So we have the steady state equations. So we need to first initialize what our initial heights and initial flow will be at time zero. So at steady state for our three tanks. So we'll have a Qn initially for a steady state and then a height initially for our steady states as well. Okay. So for our flow in, we will actually just what is it? We'll just make our own. So we can just use, I think we have to use sim. We have to use sim here. No, no, we can just make our own. So we can just have to do, I'll use what we did in class as well. Actually, I'll switch it up. So it's just applying what our initial flows in for going into our tank one and then tank two. So I'll just do 0.6 and then 0.1. Okay. And then for our height, we actually have to use minimize because for this we want to find we're not gonna get the exact height for our function of what our height will be, but we can get as close as possible so we can minimize the amount of values our solver will input to find our initial heights for our system at steady state. So we can minimize the scale basically. So we'll do lambda for our function. And then this would be respect to x. Um, and then what is it? And then x would be zero. We have our initial guesses. So this would be np dot array. And then this should be or represents it as 10, 10, and 10. Okay. Next, we will do our constraints. That's what constraints from. Constraints. And then we'll do this be type. And if I forget, I have minimize pulled up because I do forget this. So we'll be using for our minimize, we'll use our function lambda, our NP array for our initial guesses. So we'll do function, we'll do initial guesses. We'll do constraints here. That's what it is. We'll do constraints here. And for constraints, um, we will utilize type. And for our type, pretty sure I'm doing this right. We utilize type. And for our type, is it like type? How you do type? Is it type? And then we do equation. So we do equivalent. So what this is basically saying that for our type, actually I'll write it fully out. If I remember, I have to realize if I can remember this real quick. And then we do lambda again. I'm gonna just write this out and then I'll explain this later because I'm trying to explain at the same time. I'm trying to also remember what I'm supposed to do. It's not doing it. It's not working out. So let me also put this down. Right hand side, uh, 0, initial height, so H, and then Gillian, steady state. Okay. And okay, so basically what I'm saying here is, let me finish the rest. So we have bound. So we're also utilizing our bound. Okay, so bound is from 0 to np dot to infinity. Okay, that should be good. Should be a. I made to check this. I made to check this. That should be right. I think it's the type. Is it equal? I know I messed up. Yeah, it has to be equal. Constraints. Okay, but basically let me explain this and now check what the problem is because I know I messed up. But what we're saying here is that we need to utilize our function for our right hand side here. So in this lambda that we have like it's a fake equation. We're basically saying we're utilizing our x here. Okay. And x is the dummy. It's kind of our dummy. But in our constraints, we're saying the type of constraint that we have is equivalent. So EQ means equivalent. So that means this function here, the lambda function here, is equivalent to this lambda function, which we represent this lambda for our height, which will use our right hand side function, which we have to calculate our change in heights for our dummy lambda x. So this lambda x actually represents our lambda h in our constraints. Okay. And then our bound is from 0 to infinity. And I think this bounds. That'll also help. This is supposed to be equal. Okay, but I'll be back because I know I made a mistake for the constraints. I need to check, and then from there we can continue. Okay. So I just came back and checked. I'm glad I did check because there was actually a couple mistakes. So I forgot to actually pull this from the dictionary. So we had to pull our type from our dictionary. And if I read this, I think it would actually tell me that too. But where's constraints at? Yeah. So from our constraints, we have to pull it from our dictionary in Python, and then from our dictionary, we pull type and then put it to equivalent. So yeah, now it works. And then also Q and initial. What's wrong with this? Hide. Why is this? Oh, because I have to also input the function. So I have to state that this is our function. Um, then Q and initial. That's spelled wrong. Just copy and paste. So there you go. That's wrong. What's the problem there? Okay. And then also for our bounds, I need to put these in column in brackets, in parentheses. Okay. So now we should be good. Um, and I'm gonna put this actually move this back up top and then drop our functions. Okay. Shift enter. Please work. Let's go. All right, so now we have our steady state funk equations for our initial flow in for our two tanks and then our initial heights for our three tanks. Okay. Now we can actually start using our matrices. So what we want to do now is that we want to figure out what our A and B will be for our system. So A and B. Okay. And for this, like it says in here, we need to use Jacobian. So Jacobian. Hopefully, yes, perfect. Jacobian, which we'll be utilizing our right-hand side equation, and this should be the first one. And then for our right-hand side, of course, we need to have our time, which in respect here will be 0, our H initial, um, and then our QN initial at steady state. And from this, actually, it gave me a hint. I forgot to put dot X to pull in our X values that we have for our H value. So to pull our heights, we need to put dot X. So we should enter that. Now it works. So because it would we I can't talk. We would have put dot X at our H initial steady state here, but we can just do it for the function here. And then this would actually be the exact same for B. So we can copy and paste this for B. And the only thing we will change is that we'll put the 2 here. Okay. So bam, we have that. And then next we need to now run a transfer function. So this is for our transfer function. Yeah. So for our transfer function, I'll get into this now. So transfer function, like it says here, transfer function of a continuous time invariant linear state space model can be derived in the following way. The transfer function is just the derived function or derived equation from these two initial equations for our matrices, our space-time matrix, our state spacing matrices. So basically what they did here, we took our x, they derived it, and they put this for our x, and they also utilized our y's as well. So they get this as our final equation. They substitute out the u's and the g's. They substitute out the u's, and they end up with the equation at the bottom for this for our transfer function, which says our g, which g here is just a ratio of y over w of u. I'm not really sure what G used, but that's not important here. Our G is equal to C times S times I minus A to inverse of 1 times B plus D. And then remember, as I said earlier, we're not utilizing our output matrix, our output space matrix equation. So we're not using C and D. We're just using A and B. So we can actually get rid of C and D in this equation, which I'll just leave us with. And I'm going to just use our transfer functions is equal to S times I minus A to the power of -1 all times B. Okay. So that's what we have to represent here for our transfer function, this equation here. So we can actually just write this down now. So our transfer function is equal to, and then I'll put up parentheses. So we do S, and we pulled S already from SumPy. So S times SumPy dot I. And the I actually represents identity matrices. So we just want to utilize our identity. We only run an identity, we're going to multiply our identity matrices of 3 identity matrices for our 3 tanks times S. And then we subtract this. Oh no, one is inside. There we go. Minus some pi dot matrix, because remember this A is a matrix. You get to recognize that as well. So we had to, yeah. So we had to run this as matrices for A and B. So some pi matrix of A, and then this is all to the negative first, -1 power, and then we multiply this by the matrix of B. Um, and I saw matrix wrong. I just saw that. Um, Surprised he's not yelling at me. Okay, shift enter. Perfect. So now we have our transforming functions for for our system. So now from this we can actually plug in our transfer function into solve the solver, and then we can go from there. Okay. So for our solver, well, we wanted basically we're trying to find the last tank, basically the higher last tank. So we need to do it respective time and then H3. This is equal to what is it? I think we use sim now. Yeah, we use sim now. Um, I can check. Okay, so let's start. Let's input our solve IVP. Before we do this though, I did check to make sure everything was correct, and I did notice I forgot to put the at, which basically indicates that we're trying to solve for a matrix C. So we're doing matrix C multiplication instead of just a regular multiplication. So we had to multiply this matrices by this RB matrices. Okay. Now let's do our solver. So we want to represent our solver with first our time, and then we want to have the change in height for tank 3. So the deviation at 3. So the high deviation for tank 3 deep. So H3 deviation. This would be equal to sim, and then this would be our TF from 2 to 0, which is our 3 tanks. And then we'll do a lambda of t, and this will be 1. That's what lambda wrong. Okay. So now let's start our solver. This is basically just giving us our time, we have our time and our height for our solver, and then we'll be simulating this from giving our transfer function, and then our lambda is saying our time would uh be intervals of 1 for our solver. So now we do our solver. So solve IVP, we'll do lambda again. And then this would be respect to t and v, so our time and our height. And then we will oh, I keep spelling lambda wrong. Okay. We'll do a right hand side. This would be t time and then our height. And then we have our q in initial steady state. Spell that wrong? If you hear my mom, I'm sorry. She's kind of loud. Um, Hold on. They're kind of being kind of loud. I'll be back. Okay. Um, I'm back. Sorry for that. Okay, so now we're continuing with solve IVB. So we have lambda. Did I spell this wrong again? I'm just gonna copy and paste because I know I just keep spelling this wrong. So I'm just gonna input that. And then we'll also be adding an array for this. for which be representing our tank three, should be 1 and 0. Actually, I think this would be representing our first two tanks, initial flows for our solve AP. So after this, we then do our time span, which our T span. Let me move this up here so you can see better. Our T span, is just from 0 to our last time component that we have for our function. Then we have our initial guesses, which is just our height initials, steady state. Then we have our method. That's the one I'll go down. Method, which is just raw do. Um, and then this output, since this is a continuous function, we get the state that is true. Okay. So this should be good. Hopefully this works. So enter. No. Bulletin function is what's wrong? It's not this. It's not my T. No, it has to be in parentheses. What's the problem? Lambda T and our height and our right hand side, the time and height, and then we have our Q initial steady state plus the given extra flows. Um oh, because I put a comma. That's not it. Dang, I thought I had it. Okay. Um Bulletin function or method object is not subscriptable. That's what I thought. I said that shouldn't be a problem. What's the problem? I've never seen this pop up, so I'm kind of confused what to do. I'll be right back. I'm gonna see what the problem is. Okay. I just forgot to close out our bracket here for our right hand side correctly. So basically, I gotta close our NP array here, and then I need to close our right hand side of function. So now this should work. Yep, perfect. So now we have our solver works perfectly. Same is true. We have our time values that goes up to 9.9. Then we have our heights for our respective time. Okay. So now let's plot this out. So let's just fig is equal to make subplots. Fig dot add scatter x is equal to our time, our y is equal to our h3 dev plus what is it? MP I know we're supposed to add our initial flows. Yeah, our H initials of SS, steady state for tank two. So our initial height for tank two. So you have to add the change in three, the deviation for tank three plus the initial height for tank three. And this is our simulated height using our transfer function. So this is our transfer function model. This that'll be represented in our line. So I always put this as name. Um TF model. And then we'll actually just copy and paste this as well. And then we will also have, I think I forgot to put a comma. That's what it is. Yeah, that's what it was. We'll have the same X, so times still our X, but then our Y, we'll do our, we'll put this as a res. We do res, expected T, um, of our last tank. Okay. This is not our name. Okay. So now this is grabbing the numeric value from tank three using our solver. So the name for this is just our this is our just our differential equations. So this is numeric model. Okay. Now hopefully this should give us the right line, two lines. So let's hit enter. What do you mean doesn't have fig dot ax scatter? That is spelled wrong. What do you mean doesn't have fig dot ax scatter? Well, this is definitely right. Function object has no. Hold on, what? Let me see. This should be fine. Oh, it's because I forgot to put the two brackets. Okay, and then the next one is OD results is not callable. It's because I think I don't need this to. Let me see. I know some do something like this. What's the problem? Let me just not do this. Let me do solve. Let me just do solve. Let me do dot T and then no, not dot T. Let me just do solve. Let me make this may work. Solve IVP expected T -2. What's the problem here? This should work. I'm gonna be back. I don't know what the problem is. This should be right. Um, Let me check. Okay, so it was just a small mistake. I forgot to put res.solve. So yeah, so now we were good. So we if we do this, we should enter. We get the correct equation now. And basically this so the blue line is our transfer function. So we're using the matrices matrix matrices to solve for our system, and then our x is the derivation that we calculated. Um, but it should the so we're trying to compare this to see if using our transfer function will help. Would they be the same? And as you see, they are not the same. So using transfer function actually is not does not help us find our system for the change in height for tank three. So we do not use transfer function method. And the derivation is the correct way and the more accurate way to solve for the change of height in our tank three. So yeah, that's it. I know this wasn't that bad, but it was kind of a conceptual thing this time. But we are done for this part. Uh, yeah, guys. Hopefully this helped. I will see you guys for our next two parts for part C and part D. Okay, so, but I will catch you guys later.